We have been looking at signals, assuming that signals are nice and clean. But we also have to realize that signals can be contaminated by noise. But what is noise? Noise is any unwanted signal that obscures the signal that you want to observe. In other words, if you have a signal and there's another signal that comes in, if it doesn't bother you, that's not noise. But if it bothers you, then it is noise. So noise can be introduced into a circuit either from an external source or an internal source. External source can introduce noise via several methods. One of them is electric field coupling and inductive coupling. Here what we have is that the electric field and induction is generating additional signals into your pure signal, mixing it up. So this additional signal that's being injected into the waveform is not what you want, so these are noise. Then RF interference. RF interference are electromagnetic radiation. They go through the air and they can then it can be converted into electrical signals in your circuit, and your circuit picks it up thinking that it is an electrical signal that you want. So that's noise. And the source of it can come from radio transmission, which can be from your mobile phone, because your mobile phone will transmit signals in response to some weak signals that it receives. Radio can be electronic system, or even home appliances or some appliances in the office nearby. Conduction. Conduction is introduced when current is flowing through a power cable or through a signal cable, and this mixes up with your signal, so it becomes a noise. Then ground loop currents. Ground loop currents are caused because of voltage differences in ground between, let's say, two pieces of equipment. And because the voltages are not exactly 0 volts, they are not identical. If one of them is slightly higher than the other and ground paths are very low impedance, a lot of current can go through. And this will generate a small voltage drop, which should not be a problem in most cases. But if you have a high gain amplifier, then that small change in voltage drop will be amplified, and then it introduces distortions into your signal, and this distortion is your noise. Then there is internal sources or inherent noise caused by the devices that you use to amplify the signal. So this is a property of all electronic components, or all components actually. And the noise that you get is random and is unavoidable for passive components. You cannot entirely eliminate inherent noise, but you can minimize it. And you do that by good design, by knowing certain construction techniques, and by using high quality components. So we look at sources of amplifier noise. If you know the origins of the internal noise source, then you know some of the methods that you can use that can minimize the impact of this noise. Okay. Number one is thermal noise, also called Johnson noise or white noise. It is called white noise because it is white spectrum, just like light. Light is white in color because it is a white spectrum. Of course, fluorescent light is not. It's a mixture of 3 colors. But if you look at sunlight is white, but it is a white spectrum. So when we say white noise, it is a white spectrum noise. The frequency ranges from low frequency to high frequency. So it is produced by random motion of free electrons, and it is found in all components. So the noise spectral density is constant across a very wide range of frequencies. And the higher the temperature of the component, the higher is the amplitude of thermal noise. Then the second category that's quite significant in signal amplification is short noise. Short noise comes when electrons and holes recombine in semiconductors. So you know that holes in semiconductors are actually absence of electrons, so it is positively charged. We're just waiting for an electron to fill up. And when an electron fills up, suddenly there's a drop in voltage overall at that moment in point, and there's a fluctuation. So the fluctuations come like shot, like someone shooting, very noisy. And it's dependent on current amplitude. So the higher the current you use, the more short noise you will get. Then there's another noise that is known as 1/F noise, 1/frequency noise, also called ping noise or flicker noise. And this is due to random variation in the diffusion of charge carriers within semiconductor components. So when the charge carriers are diffusing through this semiconductor, it generates a noise of its own, and the characteristic of this noise is that at low frequency the amplitude is high, and at higher frequencies the amplitude is low, so it goes down. Okay, so that's the 1/F noise. So it's proportional to 1/frequency. It is also characteristic of many physical systems, and it's the least well understood among all the noise sources that we have mentioned earlier. So thermal noise. So thermal noise is caused by thermal agitation of electrons in a resistor, and it gives rise to random fluctuation in the voltage across its terminals. In other words, if you have a resistor and you don't do anything except you just put there, and you've got a very sensitive voltmeter that can measure AC current, you connect it and you will be able to find a voltage there. You'll be able to measure a voltage there. And this voltage is produced by random motion of free electrons. Now, these electrons collide with the atoms, resulting in an exchange in energy. So these energy exchanges means that the potential is no longer constant, so there is this fluctuation in energy, and that is seen as noise. But it is low level in the microvolt range. Since the noise is generated by collision of free electrons, you know that when temperature is higher, electrons are more mobile and the number of collisions increase. And when the number of collisions increase, you find that the fluctuation increases. So you now have an increased noise level at higher temperature. It is called white noise because it's a very wide spectral density. That means equal amount of energy per frequency band. So if you choose a certain frequency band and you were to shift it up to a high frequency, let's say you're measuring in the 100 Hz range, and you shift it to the kilohertz range, that same frequency band in the higher frequency range would contain the same energy. The formula for that, for a resistive element, is Vn squared equals to 4kTRB. Vn squared is your noise voltage squared. Or if you like, if you change this to Vn, then this whole formula on the right hand side will be a square root of 4kTRB. But it's more convenient to write Vn squared equals to 4kTRB, so we wrote it in this form. Okay, what is Vn? Vn is noise voltage in volts RMS, and K is Boltzmann's constant, 1.38 times 10 to the power minus 23 joules per degree Kelvin. And R is resistance in ohms, T is the temperature in degrees Kelvin, and B is the bandwidth in hertz. Interestingly, if you were to look at the maximum power transfer, maximum power transfer will occur when the impedance match, which means that if you have a resistor that is of a particular value generating the noise, and you have an amplifier that is of the same impedance, and when you connect it, there's a maximum power transfer. And this maximum amount of power that is transferred can be worked out, and it is KTB. And you can work it out yourself using voltage divider. Thermal noise dependencies. So thermal noise power is proportional to resistance. From the formula you can see 4kTRB, so it's proportional to resistance, proportional to temperature in Kelvin, and proportional to bandwidth. So as temperature reduces, the random motion of the electrons reduce and it becomes quieter. So the resistor becomes quieter. So how low can you make this? Well, you can try absolute zero. At absolute zero, which is minus 273 degrees Kelvin, electron motion stops and your thermal noise drops down to zero. So if you wanted to have a low noise amplifier, what can you do? You can put your circuit in liquid nitrogen and bring it close to absolute zero, and your noise level will drop. Problem will be where you're going to get liquid nitrogen. Okay. Thermal noise is frequency independent. If you look at the formula, 4kTRB has no F, no frequency component there. It just has a bandwidth component. Okay. So it appears at all frequencies that are of interest to your electronic circuit. It has a uniform noise power density. That means a constant power density per unit bandwidth. And its amplitude is not dependent on current flow. So to minimize thermal noise, what can you do? You minimize the source resistance. You minimize the temperature, so you keep the temperature of your front end electronics to as low as possible. For instance, if you wanted to pick up very low signals from space, let's say a satellite dish wants to pick up signals from the satellite and it's very weak signal, then the front end amplifier, what you'll do is you cool it down close to absolute zero using liquid nitrogen or some other liquid air. Then you can also reduce the noise by minimizing the bandwidth that you want to use. So the smallest bandwidth that you can get away with, you use that, and then you find that your noise level will drop.